So we'll be talking about windows. And when we talk about windows, we need to take care of three things. These three things primarily because window also brings light in. Right? You simply do not need to reject the heat through conduction, but you need to reject the heat through radiation as well. And you want to operate the window sometimes to get the advantage of convective current as well. So windows has become very complex element in a manner. So R value and U value of the window becomes important. The solar heat gain coefficient, as name suggests, is a coefficient, and solar heat gain coefficient means that amount of heat through solar radiation, not conductive, okay? Amount of heat received or passed through the window, the percentage of the difference between these two is a solar heat gain coefficient. So amount of solar gains you have one side to other side is where the coefficient works, or that's what the coefficient is. And this is only through radiation, not through conduction. If you're gaining from conduction, the solar heat gain coefficient does not account that. That's U value takes care of it. Okay? So, you have full solar spectrum, you have radio waves, then you have infrared, and then you have complete Vibrio range, and then you have X-ray and gamma radiation. And when you get what we see is only because of that, but what gets in the building through the glass is from somewhere here to somewhere there, which we don't see, but it does enter the building through the glass. Right? Or even if there is no glass, they do enter, but then they can go out as well if you don't have glass. But if it is a glass, the shortwave radiation does the radiation range changes, and then it cannot go out because the glass is opaque. Now, when I say glass is opaque to an architect, then what will happen to all that modernism when Mies van der Rohe and various people talked about transparency and translucency in architecture? To all go for a toss. Here we are just talking about glass is an opaque material when it comes to infrared range. So infrared range radiation or infrared rays cannot pass through glass, and hence we call it a glass is an opaque material when it comes to infrared. Okay? So when you have solar radiation, it's like greenhouse effect. Solar radiation gets through the glass, hits mica stone, changes the frequency, loses its strength to get out of the glass, and hence it becomes warm inside. And that is what we call the greenhouse effect. Right? So what we receive, when we deal with the fenestration, we probably need to deal with from here to here. When we deal with the daylight, Gurneet will talk about daylight, we will deal with only this much, because that's what we see. Okay? So this is where the daylighting is different than a solar radiation. So if you have various kind of glass, and what will happen is that glass will have glass have a property that at each frequency of your, if nanometer frequency of your radiation, the behavior of glass changes. Sometimes you see glass as green, sometimes you see glass as bronze, sometimes you see a blue glass. That's primarily because certain frequency gets filtered and certain frequency does not get filtered, and hence you see a color. Okay? So this is a graph. On horizontal axis you have a wavelength. On vertical axis you have radiation intensity or relative radiation intensity in percentages. And first, amount of, let's say if total amount of heat which comes from the windows is 100%, 40% is about which we don't see. 40% is from infrared. So this 40% of heat is getting in through radiation, which you actually don't need. So what happens in the glass, you need light, you need daylight, but you don't need heat. But heat enters. So actually 40% of total solar radiation, we don't need it. We can't see through it, and it adds heat to in the envelope. Right? And this is what happens. That earlier, and the rest of that is 4% is ultraviolet. So we need this much of heat, this much of light, but all this comes together is about 40% of heat. So this is where the trick needs to happen. You want light, but you don't want heat. And that's where the jugglery happens. Is this clear? Everybody? Okay, thanks. Now, and as you can see that for each nanometer, the behavior of glass changes. That if you have various kind of glass, they'll behave differently. A little bit more in detail, the transmittance value, the total solar transmittance. When I say solar transmittance, it's entire from ultraviolet to near infrared. If you have clear float glass, it will transmit in this fashion. But if you have an ultra clear glass, it will transmit in this fashion. That means your daylighting opportunity increases when you have a very ultra clear glass. But that means that it also will bring in more heat. It will bring in more light, but it will bring in more heat. Okay? Now things becomes more complex because the thermal bridging and thermal breaks become more prominent when it comes to glass, or windows rather, sorry. In walls, it is pretty okay that if you have a 5 square meter of wall, or 10 square meter of wall, at the most your mortar or your cement does not have very different conductivity than your brick. Yeah? It's not like insulation and aluminum screw. There are huge variation in conductivity between insulation and screw, not as much as between a brick and mortar. But when it comes to glass and frame, I mean, aluminum frame has a very high conductive property, versus glass may not have that many high. Hence, the U value of a glass actually does not matter. If somebody comes to you, and I don't mind giving these names to the company because we work very closely with them. If Asahi or Saint Gobain or Guardian Glass guy will come to you and say that my glass is very good, perfect, very high U value, and say that what do I do with the high value, because I am going to put this glass into aluminum frame. And your glass value will go for a toss because aluminum frame will transfer more heat than your glass. Hence, when we talk about U value, we talk about the U value of entire fenestration product and not just a glass. If at all you need to talk about U value, you say that center of the glass U value. Edge of the glass U value is different. Or edge of the wall is, the entire U value of the entire window is different. See what happens. Just imagine that I have X amount of heat is getting transferred here. Okay? I'm in the center of the glass. But when I move near to the more conductive surface, I will try to give more to this guy, then transfer, right? And this is, even in a structural system, same thing happens. So more heat transfer will take place here than here because this guy is more conductive. Hence, this portion of a glass will have an edge transfers. It will transfer this way as well, and it will start transferring to the aluminum frame as well. Right? And hence, the frame becomes equally important, sometimes more important than the glass. So, that's what we call it a center of a glass value versus edge of the glass value. And edge of the glass value is equally important. So, even just imagine that I have that wall junction. So heat transfer here And that's what we call it edge effect. That is, here the edge effect is much lesser than the edge effect here. Okay, this guy is giving it to this guy is giving it to this, sometimes this guy is also giving it to this. So it becomes very complex situation, three-dimensional heat transfer, and many things happens at one point in time. And what I am talking about is that only U value. What will happen to the radiation and convection, nobody knows. Right? So when it comes to window, you need to be a little more careful. So that's what the edge of the glass, this is the center of the glass. What is consideration is the glass, window frame, and window shutter. Now, window frame and shutter frame will become more important when you are actually operating your windows. And I'll come to that towards last part of the lecture here. So, when you have a same glass in aluminum, your U value could be 0.45. Same glass going in a PVC, your U value can drop down to 0.3. Because PVC is a low conductive material, and entire system will have a lesser glass. You have various kind of materials: wood, aluminum. That's a MS steel. Now you have a stainless steel also. You have a composite, and you have a UPVC windows as well. When you start looking at a glass, and we all know that the double glazing units can reduce the conduction, but if these double glazing units have been placed in aluminum, it is not going to help you. And hence, people have started working with a very complex systems of construction of the frame. If you ask me, in a building science, two guys have worked really, really nice in last 15 years. One is a plumbing guys. I mean, look at the Jaguar fixtures and the kind of ceramic cartridges this get and kind of foamy effect. They really work hard to give you a same kind of feeling as a warm water or cold water without using that much of water. A lot of engineering, I mean, just look at a cross section of the tap and you will realize how much engineering has gone into it. And second is these guys. Right? A lot of engineering has gone into it. So what are they trying to do is they're trying to find a way by which you can actually supplement what glass is doing. Okay, you have double glazed glass, and if there's a gasket here, you will try to make a lighter frame without much of thermal bridging or thermal breaking. At the same time, you need to maintain a structural strength of a material as well. So sometimes you see some of the metal inserts into the UPVC frames. This guy is trying to avoid all thermal breaks, although it's aluminum, but inside he has filled it up with a wood so that it doesn't become a thermal bridge. That's where the break and bridge comes. This guy is aluminum frame, but all internal is high strength UPVC. Right? So if you see the cross section, actually this aluminum does not touch this aluminum. It's all low conductive material inside. Now when you start doing this, you have another problem of convective current taking place within the cavity here. But the moment I have a cavity which is bigger than about 2 inch or 1.5 inch, a little more than that, my air will start moving inside. At the moment I get a convective current, it's very similar to the the cavity walls, sorry. Right? You have a brick, you have a cavity, you have a brick. Now if this cavity is too large, then convective current will start. The convective current will start, that means you will start doing some kind of heat transfer from this surface to this surface. So most of the time what we suggest is that you should have a ventilated cavity. So that if outdoor air is low temperature, it can enter the cavity and cool down the internal surfaces and come out of that. The next day when it has to work, at least your surfaces are cool. Even if there is a convective current, it will help you. Air will not get saturated with a higher temperature. If I really lock the air and every day I am pumping in 65 degree or 45 degree on top of it, at some point in time, that air will come to about 35, 38 degree and will saturate and say, now I cannot take anything more. So that it loses its effectiveness over a period of time. So and hence we suggest the ventilated cavity. Here also, the moment the cavity goes up, the convective current starts, and something we call it a Norsen number. We should keep that number below the 1 so that the convective current doesn't start. So this is what I'm just showing the kind of engineering now which has started getting into the windows, apart from what all happens in a glass, which I'll come to that in a while. And that's what, there are certain tools. I mean, all of you quite a few of you are aware about tools which do whole building simulations, right? You put your building in a climate conditions, you put a U values, you put internal gains, you put HVAC systems, and you do entire building for 1 full year, you do simulate. But how does it calculate heat transfer in the windows and walls and roof? There are small component simulations which has been embedded in that large whole building simulation, and one of them is a group of this window program or therm program and so on and so forth. So these are the tools which helps you to actually design only cross section of the window. And then you start looking at where is your heat transfer. You can see actually that the double glazed glass, and can you see the center of the glass value versus the edge of the glass value, which is different? This is what it is, right? As you can see, this is almost like a bridging happening here. Okay. Now, you have, when you start putting gaskets, you also need to be a little careful. So let's see this one. You have a double glazed unit with a certain kind of insulating gaskets, and 2/3 of the heat transmission in conventional double glazed unit will take place through conduction, because this is a gap, and then some kind of convection will start happening here. And based on radiation, where should you put your coating? Now, this is where the glass property will start coming in. There are certain kind of coating, whether silver or bronze coating, or low emissivity coating, we call it, low E, gets applied on a glass so that your infrared or near infrared and infrared component does not get in, but you get only solar spectrum, only visible spectrum. So what it does, that it tries to cut down on this part. This 41% of heat which comes, it tries to say that we don't want that frequency. It tries to cut from anything between 850 onwards, that frequency get cut down. That's why we call it a spectrally selected glass. The amount of which the certain spectrum only get through it, and rest does not. So what you do, you're rejecting the heat, but you are allowing light to come in. When you say light, is daylight. Okay? So when you have that kind of coating, it's very similar to what we were discussing about the insulation. Where should you have that coating? Now, problem with this coating right now is that this coating does get affected by environmental conditions. So if I have a single pane glass like this, and if I put that coating on top of it, my environmental conditions, CO2, SOx, NOx, and other things will deteriorate that, and within 3 or 4 days or even 10 days, it will go. You will not have that coating. So this coating needs to be protected. That means that coating needs to be in a double glazed unit and towards the inner side of it. Right? So this is what you see, that coating is on one side. Now, whether that coating should be here or here. Let's say, imagine that this is inner side and outside. And this is surface 1, surface 2, surface 3, surface 4. Ideally, you should have at surface 2. Because that's where, otherwise, the solar radiation will go through this clear glass, and then this guy will start coming in. It's better to start coming in as soon as possible, right? As outer side as possible. So when you, and the windows are that when you have warm outside, you need to retain a cooler inside. When you are cool outside, you need to retain warmer outside. So it's sort of double-sided sword which you need to keep dealing with. And as I was mentioning that the convective current between the cavity also starts playing a role. And that's where the U value, that's where the gravity, which affects the convective current, becomes important. So if you have a cavity about I think about an inch or so, 25 mm, a U value which you will receive will be 1.1. And the same amount of cavity, when you same glass assembly, when you turn it horizontally, your U value can go up to 1.7. Because there will be more, this is less convective current, this is more convective current. And the same thing applies in your window, in your walls and roofs as well. The thickness, I mean, when you say, oh, my U value of the wall with a 50 mm cavity is X, it will not be same for roof. Because the convective current within the cavity will really change the performance of two sides. It will start transferring more heat when it is what. So, and that's what the comparative single pane, 0.9 U value, clear glass, double pane, 0.48, and if it is insulated low E, you can really go up to 0.31. And then you start filling up with a certain kind of heavy gases, argon or krypton, and you start getting lower and lower U values. This is all engineering, not really meant for all context. If you have completely air-conditioned building, and if you are in hot and dry climate, and if you have very high window-to-wall ratio, think about these. But as Shashwati was mentioning and Professor Lal was mentioning yesterday, you should have a wall first and then start puncturing that. The way we define is that what you can do as an architect, then you start relying on certain kind of technological advances. What you can do at early design stage, and I'm digressing right now for some benefit, what you can do at a building, you can't really deal with that only with the technical fixes. We call it, you can't fix everything with the technology. Or even if you can fix, you will not have that much of advantage. Let me give you an example of how would it help? Buildings generally are meant for about 70 years, 65, 70 years of lifespan. People, when they construct, they said, okay, up to this much time we are going to use it. When you start putting air conditioning, the central air conditioning plant, probably about 18 years, 16 years kind of lifespan. And meantime, there will be a technical advancement and you will buy a new HVAC system. If you come to these kind of system, probably 7 years. If you come to light, probably 3 years. One fixture. So if you have if your tube light in your house, it will run for about 2 years and then you need to replace it. So if you don't know what is LED, and if you have put in an incandescent bulb, by some context, some mistake, whatever you call it, you have a chance to change, or you have a chance to correct your decision after 2 years or 3 years. If you go for no star AC, you don't know what is a star AC. BE has not reached out to you. You have a chance to correct that in 5 years. But if you make wrong building, 60 years flat, gone, right? So we call it a lock-in period. Certain decisions, if you do it, you are getting locked into it. And hence, at early design stage, hence the building design, what I'm talking about is all still a construction, right? This is all when you have decided the position of opening and size of the opening. After that, all this will come. But first, the sensible design will come, when to put a window, where to put a window, and what size. And then this will come. So just make sure that in the early design stage, you put in enough efforts so that your lock-in period gets into your control. Otherwise, you can't do anything. It's like, once the aircraft takes off from Delhi, you're heading to San Francisco, you've achieved about 8,000 feet of, or 10,000 feet of height, you have to land back into the San Francisco only. You can't go back and say, let's go back and land in Delhi. So you get locked in for 16 hours, right, when you're in an aircraft, versus if you're in your own car, you can always go back. So that's the kind of flexibility you have when you take certain decisions. Now, the challenge, at least in a material science, I wouldn't say latest challenge, but there used to be a big problem when we have to balance between a solar heat gain coefficient and a visible light transmittance. So on x-axis, if you put a visible VLT, visible light transmittance, and then y-axis, if you be solar heat gain coefficient, they could not produce a glass. Ideally, what you want? You want a very high visible light transmittance. You want to be here, but at the same time, you want very low solar. So you want the glass in this area, right? Now, because of the certain kind of limitation or advancement, both ways, we get a reflective glass which has a very low heat gain coefficient, which is good. It doesn't transfer much of, but it does not give you light. So that means you need to offset that with the electric light. Okay. When you go for a tinted low-E glass or only tinted glass, the blue and green glass which we see on some of the buildings, they are somewhere here. They transmit much of light, but they bring in a lot of heat as well. They are very close to clear glass, right? So, and then low E2 and low E generation 3, they are better, but again, they are costlier. So, what one needs to do, and if you have to sort of deal with this, or rather, if you have to deal with this challenge, only way you can deal is a sensible design. Where to put windows, how much to put windows. That's the only way you can meet this challenge. So, as I mentioned, low E glass, the sunlight, a long wave radiation goes back, shorter gets in, so it does not get heated up as much as the clear glass. And this is what on a graph where you have an ultraviolet range here, your visible range here, and near infrared. And as you can see, spectrally situated glass will allow only visible range frequency to get in. That means all that what gets heated up does not get in when you have spectrally situated glass, right? Most important. The solar heat gain coefficient, what all we were talking about with the low E glass, all of that is possible to achieve with a single pane glass, provided you have a good shading. The moment you shade, what you're doing is you are obstructing the solar radiation on the vertical pane, and you are increasing the solar heat gain coefficient, or rather decreasing the solar heat gain coefficient, which is beneficial to you, right? A high value or costly low E glass, double pane, is equivalent to 600 mm horizontal shade at some point in time. Because what you're doing, you are obstructing. What low E glass is doing, it is receiving first and then it is rejecting because of its surface property. Versus here you have put in a shade, which is just an obstruction. Right? More effective way of managing. So, will you put a sunscreen or will you wear a hat? Yeah, I mean, what is more cost effective? I mean, sunscreen, we don't know what's the effect it will have on our skin. We don't know what is the embodied energy of a low E glass as well. It's much effective to have a cap or a shade than going for sunscreen, right? So, if you have, let's say, and this is this graph, on x-axis, you have a angle of incident of on solar radiation falling on a window. Okay, so this means that my solar radiation is falling on the window 90. At that time, my full, this is a reverse graph, huh? So 0.8 is up and 100% is niche. I'm transferring all heat. whatever is coming from the solar radiation, versus 80-degree angle, versus 70-degree angle. So if my angle is closer to 0, I am not receiving so much of sun. I mean, impact of so much of sun, right? So that's what, so it reduces when you are closer to 0, and hence, when you start putting up various kind of shades, you are actually cutting off your solar radiation, and you are getting a better solar heat gain coefficient, right? That's the, and probably when I say that we will have another session when we'll talk about what is available, what and what kind of resources you should be seeing. If you really go to our website, carbs.org, you will find this tool which helps you to understand how shading is going to help you to understand the impact of shading on solar heat gain coefficient. So what is happening is that, let's say if I have a window, and if let me explain this graph. In a general vocabulary, we call it a heat map. Okay, this heat map has one column which has 24 cells, and it has 365 columns. So each column represents a day. The black is non-sunlit hours, and what all you see is a sunlit hours. That means during the summer time we have more sunlight hours than winter time. Each cell suggests that how much is a solar heat gain coefficient. Because the angle of the sun, solar heat gain coefficient instantaneously changes. This is unshaded window on a southern side. Yeah, it is unshaded window on a southern side. It's not written, but I think it is that. The moment you put 600 mm shade horizontal in Ahmedabad, again, all this will change the moment you change the location, right? The moment you put 600 mm horizontal shade without any overlap, that means if my window is this, my shade is this. Generally, because lintel, we do get a bit of bearing. For theoretical purpose, it is not. You can see the amount, the impact of a shade on the window, right? Immediately solar heat gain coefficient increases. What you are saying here is just the difference between this and this, right? Here the difference is much lower, and this is where it is higher. But just don't look at the last one, just look at this one, right? During the summertime, when you actually require a lower solar radiation penetrating wall, that's where it is helping you. It is not helping in sort of shoulder period or winter period, because, can somebody help me understand this? Because solar, exactly, the altitude of the sun is lower, and hence my horizontal shade is not helping you as much. So when you go for east and west side, you should go for vertical. And when you go for southern side, you should go for, single line rule. From Chennai to Simla, east and west, go for vertical with a little bit of angle. Southern side, go for horizontal. Right? So this is how all your high-tech low-E glass can be combated with the simple construction, provided you are open to accept the aesthetics given by shading devices. And you have various kind of shading devices you can have. Last point is air leakage. And do you remember my slide where I was talking about a frame and a shutter? Where was that? Window frame and window shutter frame. Now, what we are trying to do here, and most of our lecture revolves around a standpoint that we should be operating our buildings in a mixed mode operation. We don't want people to suffer uncomfortable situation in a warm summer. We would and we'll be happy to have air conditioner in our houses or in offices, but we will not use this air conditioner whenever outdoor is favorable. I should be able to open my windows or do something so that I can bring a cool air from outside to inside and make myself comfortable. So that's what mixed mode building is, sort of underlying principles going across most of these lectures. When you have a mixed mode buildings, that means you should be able to open your windows. That means when you close your windows and when you operate your air conditioner, window has to be really, really airtight. These kind of windows will not work. These windows will work only in a naturally ventilated building. It's a leaky windows. You want to save energy when you are operating air conditioner. That means when you shut your windows, it has to be airtight. And there are certain ways and certain jam conditions which you need to devise, which not only frame to glass, but a frame to frame connection, right? Not only this connection, because this connection actually sealed connection. This is open connection. So when you close the windows, it should become airtight. So when you use wood, make sure that your wood is really, really seasoned wood. Or when you use aluminum, you must have certain kind of gaskets and so on and so forth, because metal to metal connection might not be airtight. Or when you go for UPVC, it might give you a little bit of more flexibility. So this is where you can actually see that the cool air is escaping out of that area. Right? Wherever the window is leaking, the cool air is escaping. This is again a thermography image. And that's where the construction. So you may devise, so there are companies who will sell you a good window frame and shutter frame. But if you don't install it on a side, this is the area which nobody's area. Mason will say, मैंने तो ठीक बना दिया, window वाला said, mason वाले ने गलत बनाया. Right? Again, the sort of very old chain where we always used to say that when you are going on a site, you ask mason, यार इसका plumb ठीक नहीं है, इसको ठीक करो. He say, sir, वो plaster वाला कर देगा. Then plaster वाला, sir, वो लापी अस्तर में थोड़ा तो हो जाएगा. Then when you go and then the window fixing guy says, sir, इसमें थोड़ा इधर उधर हो जाएगा, but वो पेंट वाला उसको कर देगा. And then you ask पेंट वाला इसको ठीक करो, बोलते मैं क्या करूं सर, वो तो उसने ही ऐसा किया था. Right? So this is in a manner nobody's area. Hence your construction details and kind of things which you should prepare or should assist people to prepare, which is executable and it should give you certain kind of performance. You can do all simulations and all that stuff, but if on-site workmanship is not appropriate, you still will not get advantage of what all you're doing. And then some advancement in the glass, we have sort of aerogel glass, which is which is highly insulating, almost adiabatic, no heat transfer takes place through that. Or we have started getting electrochromic glass. Depending upon outdoor radiation, the glass tinting will change. If it is outdoor, is too bright, it will become sort of opaque or little. So your VLT will keep changing depending upon what's there outside. And that's what Boeing for 380 and, Airbus 380 and 747 and other people have started using it. So there's a sort of advancement which we have in a shade. Again, shading and you have movable shading. One is you have fixed shading, right? Horizontal, vertical. Second is you keep moving that depending upon your requirement. Or third is you make it automated. That moment it starts receiving solar radiation, it will start opening up or start closing down and so on and so forth. So it's called dynamic shading. So that's what all about. What we do is, and again you will see these. This is a spectrophotometer and FTIR. This is where I did show you that the roof coating we measure. Same machines we use to understand how much light and heat gets transmitted through glass, get absorbed by glass, and gets rejected by glass at each nanometer. Right? So these two guys help us to do that. That's a apparatus which is, does this mean that lunch is on the corner? This is an apparatus which helps us to understand how much air will leak from one end to other end from window frames. This is a solar calorimeter where we can fix a window here and we re-radiate the solar radiation on top of this to understand what is the solar heat gain coefficient of a window frame. If you want to understand the shading devices, you put a shading devices on top of this. So the software which we have created has a certain kind of validation from real life test condition as well. It's not just numerical, but has been validated using some of these equipment. And we will see this on Wednesday or Thursday, I don't know. So that's where we looked at the absorptance, emittance, reflectance, sorry, absorption again, but again shading, this should be air leakage. Thanks for attention. Any question?
So you mentioned about the U value, SHGC and VLT for the windows. So in general context, U value becomes a direct parameter and these two become indirect because they change according to a U value?
No.
So what my question is, let's say you choose the U value for your window.
Yep.
You want certain U value. Do you get SHGC and VLT related to that U value? Or
No.
you can change that as well?
You can change that. So U value, okay. If you want to deal with the conduction heat transfer, deal with U value. If you want to deal with the solar radiation, deal with SHGC. If you want to deal with the daylighting, deal with the VLT. Now, when you take up a glass and you want to work with the glass VLT and SHGC, there is some limitations. But if you manage VLT and SHGC together, you can get whatever U value you want to get. Okay? But this nexus between VLT and SHGC, if you want to split that, the best option is to go for shading. The moment you go for shading, you are not at the mercy of material science guys where VLT and SHGC will be dealt together. Right? Your VLT could be separate way and your SHGC can be separate way, provided you manage through the shading.
So these two properties are interdependent.
As far as glass is concerned.
If you put shading, then you can deal.
Because of the limitation of material science or glass material science. Otherwise, there is no interdependency. Yes? You will not get an answer from me because I am not a consultant. I don't want to be consultant. But what actually I can tell you is that there is no silver bullet, right? Depending upon your building use and whatever you have mentioned, all of them are double glazed, right? So double glaze is a generic where you have 2 panes or you have triple glaze, 3 panes. Now between 2 panes you can have air, you can have vacuum, you can have argon. Still it is double glazed, right? Now, which one will you apply where? It will depend upon what kind of climate you have, which orientation you're talking about, what's the building use, and what's the economics of your construction, right? So, there is no simple answer that, oh, if you go for, I can talk about that in SRI. If you go for high SRI, because the SRI deals with efficiency and comfort both together. Such generic statement cannot be given when it comes to glazing. or insulation. Because insulation and mass needs to be balanced out, glazing and shading needs to be balanced out. So there cannot be, like SRI, one cannot have a single liner advice.
Taking an example, G plus here, G plus 4, G plus 4, the topmost flat gets heated up ready. It's already ready. What should we prefer to decrease the solar radiation from the roof? SRI coating on the roof, or to use the cooler system on an existing roof? What will affect more at a cheaper cost?
I think I'm not in position to answer. All of these are now equipped to answer that question. Can somebody attempt the answer so that I know whether you're just watching or you're gathering? I think somebody should try to answer this question. I will ultimately, but I just want to some test for all of you. Yes.
Actually, SRI coating will be the better option because it will be cheaper. And what you are talking about the radiant cooling system, you again need to check about the, you need to check about the area of water capacity, whether dense or not. Again, the climate also affects. Like in a hot and humid climate, there is, if I say you won't get that much effective work even if you're using on radiant cooling. So it's a simple daily building, no radiant cooling, and I just want to compare the impact of SRI and the traditional impact of cooler.
Okay. Let me try to address this. This is what you need to do. I'm not answering you, but I'm just saying this is what you need to do. Okay? This is Delhi, you said. Okay. Try to find that what is the temperature variation from outside and desired inside temperature. Okay? Based on this, and I assume this is a flat, so you will be opening your windows. Okay. Based on that, find, do you need insulation as a priority, or you want to reject radiation? You just have 5 rupees. You say that 5 rupees, whether should I buy a cooler or should I buy a paint? So you're based on what is inside outside temperature variation on one side, which will decide whether you should put cooler or not. Second is how much radiation is falling on your surface. Okay? So heat transfer through the radiation and heat transfer through the conduction, you will calculate. Once you calculate it, you try to improve both the cases and then decide that 5 rupees worth for paint or 5 rupees worth for cooler. This is what you will do. Okay? Okay. Sorry for not answering, but this is what you need to do. This is not, I like these questions, but I will take my own stand. This is not a, Griha, IGBC, BEE awareness program that you ask question and I'll give you answer. This is a training program. At the most, we will tell you this is how you calculate, you will get an answer. So this is gone. One point which I forgot, which was not related with energy efficiency, but it's something to do with the stability of double pane glass or structural stability with double pane glass, is when you choose double pane glass, make sure that the thickness of both pane are different. Okay, so if you're choosing 3 mm, don't go for 3 mm, go for 4 mm or less. The reason for that is a reverberation time of both glass would be same, and if for certain reason, if the reverberation time somewhere else matches with the reverberation time of one glass, both glass will break at some point in time, right? If it is thickness is different, that means the reverberation time is different, and you get a better stability for the double pane glass. So this is more to do with the acoustics and structural stability part than energy efficiency, but it is important to go for two separate thicknesses for double pane. Shall we break for lunch? Samir? Yeah, okay. Thank you. I'll see you tomorrow. I'm around, but we'll see you tomorrow.